Class, I want to talk to you a little bit about Chapter 6. I talked to you a little bit about Chapter 5 in my last video, which I believe was in two parts. And in this particular chapter, we're talking about probability sampling. This is another really important concept in inferential statistics. Basically, what it all boils down to is that a sample, when it's picked from a larger population, has to be representative of the sample from which it was selected. In your book and in all statistics books, that's referred to as picking a sample based on EPSEM, EPSOM, equal probability of selection method. When you do that, you have a probability sample when a sample is of a sufficient size. And for your author, a sample size of at least 100 is sufficient, 100 or more. Less than that would not be a good probability sample. One of the reasons we want to make sure that our sample can be defined as a probability sample is so that we can use all of the theories and theorems that go with probability theory. Once we do that, we can make an inference about our sample from the sample to the larger population, which is the whole point to inferential statistics. When we want to know if a particular program worked for 5,000 people, we pick a small sample from the 5,000, maybe 100 or 200. If that sample's representative, then we can find out whether or not our sample finding is relevant with regard to the larger population. In other words, how right or wrong were we? We would have a known margin of error available to us, and so on. And this is why probability samples are so important. If you had a non-probability sample, a sample that is either too small or not representative of the population from which it was drawn, then none of the mathematical theories or theorems will apply. I'm not going to go into each method for picking an equal probability of selection method sample. They're spelled out quite nicely in your book. But I'll just mention them, okay? Simple random sampling, systematic random sampling, stratified random sampling, and cluster sampling. Those are all ways that you can get a probability sample. They're all methods. You may have learned these things if you had social research. If you didn't take social research, I'm sure you'll learn them when you do take it. So these are ways that we can, there's not just one way to pick a probability sample. There are several, and I just named them, and they're discussed in your book on pages 146, 147, and 148. Okay? Now, there's a difficult concept in this chapter that's brought up, and it's called the sampling distribution. It's really an important concept. It's not a sample, okay? So get that thought out of your mind. The sampling distribution is a bell-shaped curve on a graph, obviously, that is made up by pulling an infinite number of samples from a population. So, for example, if I had 1,000,000 people and I wanted to know what the average age was of the 1,000,000 people, and I pulled a sample of 100, I would calculate the average for my sample of 100. I would put it back into the million, and I would plot that answer that I got for the first 100 on the graph. Then I would pick another sample of 100, and obviously it wouldn't be exactly the same as the first, so I'd get an average age for that second sample, and then I'd plot that on the graph and put my 100 back, and then I'd pick a third sample and a fourth sample and a fifth, and go on infinitely. I say infinitely intentionally because the sampling distribution is a theoretical concept. It's not empirical. It does not exist in reality, all right? Because you could never pick an infinite number of samples. Obviously, you'd never finish. But what the mathematicians tell us is that if we were to pick an infinite number of samples, and we were to take that mean average, or the proportion, if we're looking at a proportion, a mean or a proportion, and we plotted that on a graph, and we did that an infinite number of times, we would get a bell-shaped curve that is normal in shape, right? And also, the sampling distribution, theoretically, would have the same mean average age, in my example that I was just using, as the average for the real population. So that's a key concept. It's a theoretical concept that mathematicians have tried to prove over and over again. We don't need to get into the math of that. But when you create this sampling distribution, you're actually creating the real population mean, okay? That's really critical. This is discussed on pages 149, 150, and 151. And it's really important that you pay attention to that, read it, understand it, and practice it. If you have questions about it, I want you to bring them to my attention so that I can help you. But the sampling distribution is not an easy concept to grasp. It's not hard really, but it's hard to grasp. And it's the sampling distribution that links our sample to the population. Remember, we pull a sample so that we can know something about the population that it was pulled from. But if we can have this sampling distribution in between our sample and the population, and then locate our sample somewhere under that curve of the sampling distribution, what we're told in probability theory is that we would essentially be doing that. What we would be doing is the same as what it would be if we were dealing with the real population, which we cannot because it's so large. Again, bring issues like that to the fore so that we can discuss them and clear them up, okay? And that's all I'm going to say about this right now. It's not a long chapter, but it's an important chapter. Pay particular attention to the sampling distribution and how the sampling distribution is the linkage between your sample and the population. Good luck, and keep hard working in this class. It's going to be a short semester, so it'll be over soon.